Good morning. Looks like we have another midterm coming up. It's nearing time for midterm 3. So here's a set of problems. We've seen these before. These are from previous year's exams. So let's go through some of these and kind of talk about what the expectations are and tie these in with everything we've been looking at in class. Laney is here for the review. I'm going to set Laney out to the side here. All right, but let's go ahead and let's take a look at these problems. And so, let's see, the first problem that we've got here, it looks like this is a Schrodinger equation for hydrogen. So this is the real deal, right? We kept saying that in lecture, that, we had done the Bohr model, but the Bohr model wasn't really correct. And so what we're going to do now is we're going to find quantum states for the electrons in hydrogen the quantum mechanical way. We are going to work from the Schrodinger wave equation, and we've got it set up so that it's representing hydrogen. The potential energy term in the Schrodinger equation here is a single interaction between a proton and an electron, or a nucleus and an electron. So there's just one interaction. And then the other limitation here is we've left out all the angular dependence. So in the problem it refers to a radially symmetric Schrodinger equation. And we mostly worked with this in class. We said unfortunately the wave functions get really complicated if we start looking at some of the higher energy levels, things with more angular momentum. So for the most part we stuck with these wave functions where there's no orbital angular momentum in the setup. So it said here is a wave function, so this is representing a quantum state, and it's asking us to plug that in and test it out, see if it really does satisfy the Schrodinger equation, and if it does, determine what are the values for the energy. We'll get that by plugging it into here. And then also, what we're going to end up doing is get this scaling factor. Now the scaling factor, I'm going to call this little a. It is, at this point, we don't want to call it the Bohr radius because we're starting over afresh, and we're doing this quantum mechanically. So there's, get the Bohr radius out of your mind. This is actually how we're going to determine the scaling factor for our wave functions from the Schrodinger equation itself. So that's the intention here. So let's do this. Let's show that it really is a solution, or maybe it's not. Here is the Schrodinger equation, the radial version. Remember, we are going to have, oh, I guess it's here. This is already a couple steps in. So I'm going to refer back to this. We need a first derivative of the wave function, and we need a second derivative. Both of those are showing up in the kinetic energy portion. So this is the kinetic energy portion of the Schrodinger equation, and we need both of those first derivatives with respect to r. So the wave function is pretty straightforward. It's just a straight exponential drop-off. In fact, I'm guessing you guys already know which state this is. I'm hoping. It's the 1s state. So we spent, I don't know, more time looking at the 1s state than any of the other states, all the other states combined. So this is the one that you guys should recognize immediately. So anyway, it's a pretty simple function. We can take a first derivative and a second derivative of that pretty easily. Now notice, we've talked about this too, when I take the derivatives, I'm actually able to write the derivatives in terms of the wave function itself. And we said that can make the whole process a little easier. It's not guaranteed that's going to happen. It doesn't have to have it satisfy the Schrodinger equation. But with this wave function, it does. And so I can take these expressions for the first and second derivatives, plug those back into the kinetic energy portion of the Schrodinger equation, and this is what I ended up with. So let me try that again. Take the first and second derivatives, plug them into here and here. When we plug those in, we get this. Sorry, I skipped that first step. I just referred back to the written problem. So this is what it's going to look like once there's taking the second derivative did that, taking the first derivative left us with this. All right, now when I look at this equation, what I can see is the wave function here and here and here and here, and each one of those four terms, the wave function factors out. I can just cross out all those wave functions, and what we're left with are two constant terms and two terms that behave like 1 over r. So those are the two types of terms that we have. Now, if it's truly a solution to the Schrodinger equation, the constant terms have to match up. Now, the constant terms would be the e, remember the wave function factored out, is equal to minus h bar squared over 2ma squared. That needs to be met, that condition, if this is to be a solution. Now, that's only one condition. Now, we haven't determined the scaling factor and we haven't determined the energy. So actually, this is not enough information yet to determine those. Let's move on and look at the other condition. The other condition is that the 1 over r term from the potential energy needs to somehow cancel out. And it will cancel out because we have a 1 over r term here. So that's what has to happen anytime we take the Schrodinger equation. We put a potential solution in there and see if it really works. If it does really work, we will see these terms match up. So the 1 over r terms, I took the coefficients. The h bar squared over, now the 2's cancel, so it's over ma, is equal to ke squared. Now what that does is it gives us one condition. This does not include energy. It only includes little a, our scaling factor. And so what that does is allows us to go in and determine the value, you know, algebraically or in terms of physical constants. The scaling factor depends on the Planck's constant, depends on the mass of the electron, depends on the electromagnetic force constant, and it depends on the charge. Now, what's kind of interesting here is what happens if, in nature, the electric force were stronger? What if the electric attraction between the proton and the electron were a larger value? What effect would that have on our wave function? And if k were larger, a would be smaller. And this is telling us exactly by how much. So that's kind of interesting. It actually physically is telling us that the size of atoms depends on the strength of the electric force. If the electric force were stronger, atoms would be smaller. The electrons would be drawn, the electron wave functions would be pulled closer to the nucleus. All right, so I fiddled around with this. I could have just put numbers in here, but I tried doing some shortcuts and it became kind of a toss-up. I'm not sure if I made it simpler or just more difficult. Anyway, it did use our old familiar shortcut values of Hc, 1240 eV nanometers, mc squared, there's the mass of the electron, and Ke squared, we haven't used that quite as much, but that's a good shortcut also. And Ke squared is 1.44. And it has the same units as Hc. So putting all those in, we find that the value of the scaling factor is 0.0529 nanometers or 52.9 picometers. So we have determined the scaling factor for the exponential drop-off of the 1s state in hydrogen. And yeah, that happens to be the same value of the Bohr radius, but Bohr got it using incorrect assumptions. All right. So this is, you know, to our understanding currently, this is the correct way to determine what the value of A is, and that's what the scaling factor worked out to be. Now, since this gave us the scaling factor, this condition from the 1 over r terms, we can now use that value of A and establish what the energy is for this state. And to no surprise, plugging the numbers in on that gives us, I hope it's not a surprise. You guys aren't surprised by this, right? I hope. So you kind of, if you were on any, you know, if you're taking the midterm, which you're going to be doing very quickly, very soon, not quickly, you're going to be taking the midterm at a good pace. But in the near future, you'll be taking the midterm, and if you got a number other than negative 13.6 eV, you should be a little concerned, okay? Unless something else was different in the problem. If it's a straightforward 1s state for hydrogen, you kind of should be familiar with that. Let's see. And so we're going to say, yeah, it's the 1s state, and that's what it looks like. And if we squared it, we give it a probability. But we got the values, and we got them the right way. We got them the chapter 39 method. We got them by using the Schrodinger equation. All right. Okay, let's move on and take a look at this next problem. Now, here is another problem, actually, taking a look at the solutions from the Schrodinger equation. And what it's saying here is, let's see, if we were looking at a one-electron atom, not hydrogen, but let's say helium with an electron missing, or lithium, in this case, lithium with 2 electrons missing, well, that would change the charge in the nucleus. What do we have to do to the Schrodinger equation to take that into account? That only affects the potential energy term. It doesn't affect the kinetic energy of the electron in terms of where the value of Z needs to go. So I can take Z equals 3, put a factor of Z right here in the potential energy, and we're done. Or we're not done. We have to go back and solve the Schrodinger equation again. So if we do that, if we put a factor of Z in here, let me move on to the solution. I guess I need to be on the next page. So here we go. Here is lithium with 2 electrons missing. Z is equal to 3. The energy we've gone through and solved, we've gone through and shown that everywhere we used to have a factor of Ke squared, we will now have a factor of Z Ke squared. So we can see that from the formula here, right? If we put a Z here, Z connects with Ke squared, those are going to go together. That tells us we're going to have 2 factors of Z. Or we can go back and solve the Schrodinger equation all over again, okay? Which would be a good exercise. But remember, it's a midterm, so we're a little limited on time. So if we can just recognize that changing K to ZK leaves us with this, here's the formula that we had worked with before in class, minus 13.6 EV Z squared over N squared. Now remember, this only works for atoms that have 1 electron remaining. All the other electrons have been taken away. That greatly simplifies all the interactions taking place in that atom. If I only have 1 electron left, then there's only 1 interaction that we have to be concerned with. So in any case, putting the 3 in for the Z, that gives us 3 squared is 9, 9 times the energy. That's a significant difference. When I now look at the 4 states, which it tells me to do, those energies are 9 times deeper than they were with hydrogen. And by 9 times deeper, it's 9 times as much binding energy. The electron is being held in those quantum states much more forcefully, a deeper potential energy by a factor of 9. Now it asks, so we can calculate the energies using the formulas, see how deep those are. If we had a photon transition from 3 to 2, that now represents, let's see if I got this right, this is minus 13 down to minus 30. So that drops by 17 eV between state 3 and state 2. That puts us off into the UV by a good margin. The wavelength on that is at 73 nanometers. That also tells us it's off in the ultraviolet. Now, I don't know if you guys remember, but in hydrogen, 3 to 2 transition was much less energetic. It was in the visible part of the spectrum. So it was, a couple of EV instead of now it's 9 times as much. Okay, so it is just that factor of 9 that carries through everything. Now in part C, so that seems all fine. Now D seems to be, D makes sense. So now what we're saying is what happens in terms of orbital angular momentum. When we move to something other than hydrogen, how does that affect the orbital angular momentum of the electron? And it doesn't. So that's kind of curious that it had a big effect on the energies, but it's not having an effect on the possible angular momentum. Those angular momentum states are unaffected by this. And so, what did it say? It says, let's imagine we're looking at a 3D state. Now the 3 I can kind of throw out. I don't need to keep the 3 around. That's giving me information about energy. But for the D state, L is equal to 2, little l, the quantum number. And remember, the total amount of angular momentum given by L plus 1 square root times h bar, that's 2.45 h bars. Along the z-axis, it can have any m sub l value between -2 and +2. So that's 5 possible orientations. Now I drew this little diagram. I don't think it asked for it. I'm going to get extra credit, I think, maybe. So I drew this angular momentum diagram. What this is saying is that, this is the xy plane for angular momentum, and then the vertical axis is representing the z component. So in quantum mechanics, we can pick one axis, and kind of by convention we call that axis the z-axis. And then what we can do is we can have no units in the z direction, and that would keep all the angular momentum in the xy plane. That state would be an m sub l is equal to 0. The 0 telling us none of the angular momentum is in the z direction, it's all in the xy plane. But it doesn't give you any additional information, so we don't know where the angular momentum vector is pointing within the xy plane. Similarly, if we jump up to this level right here, that corresponds to m sub l is equal to 1 plus 1, and that says that we've got a certain amount in the z direction, and whatever's left is spread around the xy plane. So that's what this is representing. This is the m sub l is plus 2 level, and again, any residual angular momentum is going to be in the xy plane at that level. And then it's just the same in reverse, I guess, with negative signs. So what we can do is we can go through and define what's the angle of orientation. Now, angles of orientation are a little funny because mathematically, it turns out it's I want to say, in most problems, it's useful to start at the z-axis and measure the angle away, and that's what theta does. And that is kind of our convention. When we're carrying out integrations, we tend to do that. But there's another option, and that is, instead of calling this, I shouldn't have called this phi, I apologize, I should have called it something else, alpha or beta or something. I could go back and call that alpha. Anyway, because usually we're thinking of phi as being the xy plane angle determiner. In any case, this is the complement, is the way I'm using it in this problem, as 90 minus theta. And that's more of a latitude kind of thing, right? Where the equator is at 0 degrees, and then as you move away from 0 degrees, that angle is increasing. Okay. And so I wrote down, I solved for the angle by saying the cosine of theta would be Lz over L. Well, if the cosine of theta is Lz over L, the sine of the complement of theta, which I'm calling phi, which was not a good choice, is the sine of phi would be equal to Lz over L. Anyway, I went through and solved both of these. I actually solved these and then just subtracted them from 90. Yeah, took 90 and subtracted it. And then I wrote in the LZ values. And so the nice thing about the phi approach, using the equator as 0, is that you can see the symmetry. You can see how the plus 1 and minus 1 states are evenly shifted in terms of orientation, as are the 2 and the minus 2 states. Okay, so be ready. You guys should know your angular momentum, both orbital and spin, and you should also know your way around the some of these energy formulas. Okay. All right. Let's move on from that. In problem 3, what we're doing is we're looking at a diatomic molecule. So this is chapter 40 that we've moved on into, and in this particular problem, we're looking at oxygen. We're looking at O2, and they give us a bond length, which is kind of standard. We're used to seeing bond lengths. It does say that each of the oxygens we're looking at has a mass of 16. Now, you might be thinking, well, of course, that's what the periodic table says, but we can't work from the periodic table for individual molecules, because there are other isotopes of oxygen. I believe, it's most of the oxygen around us, most of the naturally occurring oxygen, most of the oxygen is the isotope is 16, but there's an 18 isotope, maybe there's a 17 isotope too. And those with different masses, those molecules with oxygen nuclei with different masses would have different properties individually. So the properties aren't going to get averaged over. Either you're a 16, an O2 molecule with 2 oxygen 16s, or you're not. If you're different isotopes, you'll have different vibrational properties, different vibrational quantum state energies, for example, just by a bit. Not a huge effect, at least not in oxygen, I guess, but measurable. You can see this as separate peaks on measurements. So for this, let's see. Now what's unusual in this, they gave us the bond length, that's pretty standard. They gave us the isotopes, but they also said that the amplitude of vibration has been measured to be 5.1 picometers. So the bond length is at 120, but that's not fixed. So there's a little variation. If we did, a series of measurements trying to find out where the bond length is, sometimes we would find it, around 120. Sometimes it might be a little higher, sometimes it might be a little lower. And the variation that we see is like 120 picometers plus or minus 5.1. And so that's what they're telling us. So let's take a look at this. Now, I'm going to start out, I think it starts out with rotational energies. Part A is asking about rotational energies. So here is our standard diatomic picture. Here are the 2 nuclei with masses M1 and M2. I've got those designated as 16 atomic mass units. Now, the formulas we've worked with are in terms of something we call the reduced mass. So I had to determine the reduced mass for the system, and then I used a conversion, I should have written it down here, I didn't, between atomic mass units and kilograms. So make sure that's in your notes. Unless you've absolutely got that memorized, make sure you can convert back and forth between atomic mass units and kilograms and grams, whichever you're asked to do in a problem. In this problem, I'm trying to get everything in standard units. So I'm going with kilograms. Now they've told us the bond length, and they've told us the variation in the bond length in terms of picometers. And so the formula we have here is h bar LL plus 1. Now it was J over here. J gets used for angular momentum, and I think this problem was taken out of a different textbook. And so that's got J in it, but I went back to L, which is what we've been using. I just plugged the numbers in, and I ended up with, for the 0, 1, and 2 state, remember with rotational energies, it's possible to have no angular momentum. That means it's possible to have no rotational kinetic energy. The first excited state has 363 micro eV, and the second excited state, according to our formula, is at 1089. Let's move on to vibration. The vibrational formula that we worked with for diatomics is this, where V is the quantum number, and we want to find the 0 and the 1 and the 2 state from that. Now this one's different because this is not in terms of amplitude of vibration. So what I had to do was search for a way to bring that information in. This 5.1 picometers is trying to tell us how we would go about determining the energy of the vibrational state. So I started playing around with some things, and first thing to recognize is omega is, the angular frequency is k over mu. In fact, we said omega, there's not really something following a trajectory here. It's quantum mechanics. And so omega is just kind of a carryover from classical physics, which doesn't really conceptually apply, but it's a handy mathematical number to plug into our formula. So omega, in any case, k over mu square root, I flip that around, so k is equal to mu omega squared. And then I said, okay, the amplitude they gave us was for the ground state. So I said if we're in the ground state, then the energy of the ground state, V would be 0, would be given by 1/2, I guess I'm up here, would be given by 1/2 h bar omega. So I wrote that here actually. And then I said that would be the same thing as 1/2 k amplitude squared. So that is a formula, again it's a carryover from classical physics, as to how do we define amplitude of vibration, and we can write it as a potential energy. So again, physics 4a, little bits of physics 4a coming in. And then what we can do is take that k out. Now this is what k is this. Is it Boltzmann's constant? No. Is it the electromagnetic force constant? No. It's the bond stiffness. And so, and you know, in class we've been trying to emphasize more bond stiffness, more so than omega, as something physically meaningful. So there is a rigidity of a chemical bond, depending on how the electrons have arranged themselves around the nuclei on either side. Nuclei, if it's a floppy molecule, then the nuclei can move back and forth and the bond length changes a lot. But if it's a very stiff molecule, the nuclei can't shift much. The electrons are really holding the nuclei in place. So if you've taken chemistry, like double bonds, triple bonds of, you know, kind of the molecules on the smaller side, things like O2 or N2 would be even higher values of K, or carbon monoxide you may know as a triple bond. So those have very high values of K. The electrons have really wrapped themselves around the nucleus, and they're not going to move back and forth much. So anyway, I took that formula, that extended formula, and I took the last two terms, and omega, it said, can be thought of as, well, it's equivalent to h bar over mu a naught squared. So now we've got something, we've got omega expressed in terms of a naught, and that's what was given to us. So the formulas actually at that point look pretty similar. Look at that energy of rotation, h bar squared over 2 times the reduced mass times the bond length squared. Here, h bar squared over 2 times the reduced mass, amplitude of vibration squared. So I kind of like that. I like being able to see that the formulas really are almost identical. The pattern of the quantum numbers is different. This is LO plus 1, this is 2V plus 1. Anyway, putting the numbers in for this, I ended up with 0.1, 0.3, and 0.5. So with vibration, as you guys are familiar with, the ground state in vibration already has kinetic energy. You can't eliminate all the kinetic energy of vibration. There will always be residual energy of vibration in any chemical bond. There's always a little bit of energy of vibration present. Okay, now my warning on these kinds of problems, because you guys should know these kind of problems kind of inside, outside, flipped over or whatever, upside down. You've got to really pay attention to units. Okay, they're deceptive. They look like, hey, it's just a plug-in, what could possibly go wrong? But if you've practiced these, you know, and the secret is to practice them. If you guys have practiced these, you know, oh my gosh, I made an error. Oh my gosh, I left that factor out. Oh, that didn't get squared. Oh, I never got joules converted into EV. There's a number of places where you can go wrong, and that's what the problems are about. So, coming up and saying, hey, but I set the problem up the right way, I just got all the numbers wrong and all the unit conversions wrong, that counts for a lot. Okay, so setting up the problem definitely counts, but being able to carry through a problem like this and keep track of all the units and keep track of all the factors of everything and know what the symbols are referring to, that's huge. Okay, so make sure you can do all aspects of this sort of problem. Okay, that's my warning. It sounded kind of warning-like, right? All right, problem 4 is this. We're still in chapter, so at 39, 39, 40, 40, this must be 41. This is still in chapter 40, we're looking at molecules and this time solids, in particular metal solids. And we spent, we kind of drilled down we kind of went kind of deep into the mathematics in some of this stuff with electron states in metals. And that's because it's used a lot, and it's a good chance for us to go in and look at a more complex system of quantum states for electrons. And you guys are definitely going to see this in your upper division classes. Even when you do, when you take properties of materials, you'll see these kinds of references as to how the electrons are being arranged. So in sodium, now this is metallic sodium. It's not a shaker of sodium chloride, of salt. It's metallic sodium. So the first thing we have to do is make sure that it's like in a nitrogen atmosphere, so that there's no water or no oxygen around that it might react with. Because a block of sodium metal can react violently. If there's nothing for it to react, then it just looks like a block of metal. All right, so a nice shiny piece of sodium metal. And looking for this problem, the first thing we do is we start looking at the electron configuration to identify which band of electron quantum states we are going to be looking at. And the state we're going to be looking at are all of the 3s electrons. So the 3s electrons, instead of being assigned to individual atoms, are assigned to the whole block of metal. We can treat the 3s electrons, wave functions, as being spread over the entire block. That's kind of remarkable. And it matches our observations of how these metals behave. And so the first thing we want to do is now little n is actually number per volume. And so I've taken the density number, and I've taken the molar mass, and I've taken a units conversion, and it's a volume here, so I had to get 3 factors, and I hope I did all that right. And what I ended up with was, for a block of sodium metal, given these density, oh look, this would float in water, except that it would react with water, so we don't want to do that. 25.4 atoms per cubic nanometer. So I find, as you guys know by now, I like to use nanometers, I like to use picometers, rather than lots and lots of scientific notation. And cubic nanometers are a good size to count atoms, because the atoms are like a few hundred picometers across, and that means if you take an entire nanometer cubed, it's going to fit some comfortable number of atoms in there, and this time it's 25. And so since we're looking at 1 electron per atom, that's what we're seeing with the electron configuration. The number of electrons per volume for the 3s band of quantum states in particular is going to be that very same number, 25.4. So I just pulled out the formula. Now we derived this, and unless a problem tells you have to derive it, which it won't, then I can just pull the formula out that we've been using and say that the nth state, I can plug that number in and put all of these numbers. I've got the number per volume set up now, and I can solve for what the Fermi energy would be. So the idea here with the Fermi energy is if I count the electrons all the way to the top, which is kind of what this number is doing, that 25.4 electrons per cubic nanometer is going to be counting all the electrons. That's what the Fermi energy boundary is. So I can calculate that Fermi energy value by taking the number that we determined here and plugging into the formula. I got 3.15 eV. I think the example we did in class was copper that was like 7 eV or something. So this seems fairly reasonable for a Fermi energy. So it should be, several eV, something like that. Now, it says, okay, fine, in this block of sodium metal, it's 1 cubic centimeter, so 1 cubic centimeter is like, it's a cubic centimeter. So it's worth stopping, looking at your ruler, seeing what a centimeter looks like, and imagining a cube that size. How many electrons are in there? And how many of those electrons would fall within a certain range of kinetic energies? Now, the the way we're getting these wave functions, we're only really considering the kinetic energies of these. And so the kinetic energies we're finding are going to run between 0 and, the Fermi energy. There may be some with a little more kinetic energy, but Fermi energy is where we're going to really see above that in terms of kinetic energies. Those states just aren't going to be filled for the most part. And so we had worked with this density of states function, and what we found is if we integrate from 1 EV to 2 EV, which is what the problem's asking for, we should just be able to count the number of states. Now, we can do that, but we said that there's an easier way. What we can also do is just invert this formula, put in a value for each of the energies we're interested, 1 EV and 2 EV. If I solve that formula now, it will tell me how many states we've how many states we've counted through in order to reach that energy. So if I look at the energy states and I start with 0 kinetic energy and work my way up to 1 EV, it tells me for a 1 cubic centimeter of sodium, I will have counted up to the state 4.54 10 to the 21st, which is a really big number. And then it says if I now count all the way up to 2 EV from 0, again starting from 0, plug 2 EV into here instead, that gave me 12.84 10 to the 21. Now they want to know how many states are between those two values. I can just take a difference. So it says 8.30 10 to the 21 states. Now this is so far below the Fermi energy, these are all going to be filled, right? We found that every state is filled almost 100% certainty until you get within a couple tenths of an EV of the Fermi energy, and then you start to see missing electrons, and those missing electrons are in states just beyond the Fermi energy, but that happens over a pretty narrow region of just, again, tenths of an EV. So we're well below that. These are all going to be filled. Okay. So take a look at these bands of electrons in metals. That's also, we've looked at a number of examples of those. So I think we can squeeze in this last problem. So problem 5 we'll do, and then we'll take a break and we'll come back and flip the page over and do the other 5 problems. But let's take a look at this problem here, 5. So we're into chapter 41. We're looking at nuclear physics. And in particular, we're looking at radioactive decay. It's beta decay, and they tell us it's nitrogen-13 beta decaying into carbon-13. And I think pretty sure that was an example that we used in class. So it says write down the reaction, showing all the particles involved, and then it kind of steps to the side for a minute. So this is I'm hoping this is not a difficult problem for you guys, but the reaction would look like this. Now we added some things in that we said are really important in problem solving. And so for beta decays, what we always did is we wrote the underlying reaction. Now if I'm going to beta decay from nitrogen-13, which is nitrogen is element 7, I'm going to go back to element 6, which is carbon. Well, that says I'm going to lose one of the protons, and that means the proton is going to convert into a neutron. Okay, and if you're hearing that for the first time, ooh, okay, the midterm's coming up. So get back and study this chapter. So protons are turning into neutrons, and the reaction that's coupled to that is the formation of an electron and a neutrino. Now, electric charge is conserved, which says that if the proton, which we started with, was positively charged, which protons are, then the electron coming out would be also positive charge. So it would be an anti-electron, or what we call a positron, or what used to be called a negatron. And that's another interesting story. So we've got these negatrons, and we've got some sunlight on the screen. Let me go ahead and block that off. I see the sun has shifted. Sorry about that. So that is so much better. So let's go with this. Anyway, this is the reaction, and what we did was charge balance. What we said is let me finish it up. So if this is the antiparticle, then the neutrino is the particle. Okay. And we haven't done chapter 43 yet. We're going to find out that neutrinos come in different flavors. You don't have to worry about the subscript E right now. It turns out it has to be what's called an electron neutrino, a neutrino that is associated with the electron most closely. Not an issue for us yet. That problem, midterm 4, that will become an issue. Now, the high energy particles coming out are going to be the electron, which got cut off, and the neutrino. But when we look for charge balancing, we find out that we have an extra electron on the carbon. So what we do is we disassemble that and say, I'm going to start with a neutral carbon. This 6 is still there, with an E minus, an E plus, and a neutrino. Okay, so I hope that looks familiar from class. That when we do beta plus decay, which is what this is, we're going to end up with 2 extra electrons and a neutrino. One of those electrons is still associated with the atom. One of them was generated in this fairly high energy reaction. Now, part B of the problem kind of goes back to a different part of the chapter entirely, moves away from nuclear decay, and goes back and looks at binding energies. So the way we calculated binding energies, we counted all the individual protons, neutrons, and electrons. Let's look at nitrogen-13 first. Adding up the masses of that many protons, this many neutrons, this many electrons, and their masses are given there, out to 10 significant figures, for the proton and neutron at least, down to billionths of atomic mass unit. I ended up with 13.106764 atomic mass units. Now, when we look at the completed nitrogen-13, that's 13.005739. I hope all of you who like lots and lots of significant figures are really enjoying this chapter. And so I subtracted that off 0.101025 atomic mass units. Using the 931.5 conversion, that becomes 94.1 MeV total binding energy. And then if we divide through by the number of nucleons, that becomes 7.239. So that gives us an idea of whether or not we've made a mistake in the problem. We said all the binding energies that we calculate are probably going to be between 5 and 9 MeV per nucleon. That's just the range of nuclear binding energy that we see in all the nuclei that we've ever looked at, and so, or ever will. So if you see something outside that range of like 5 and 9, 5 on the low end, 9 on the high end, except for deuterium. What's the binding energy on deuterium? That one might be lower. If it's over 9, something went wrong. Okay, so watch for that. Let's see. Okay, I guess that's it. The carbon-13 works out the same way. This time we have 6 protons and 7 neutrons, and that means the mass here is a little different. When we look at the mass of the completed carbon-13 atom, that's also a little different, gives us a little bit of missing mass difference. The binding energy is a little higher here, and the binding energy per nucleon is a little higher. And doesn't always have to be the case with these beta decays, but for the most part, when you have a radioactive decay, what you're going to end up with is the stuff you end up with will have higher binding energies than what you started with. Okay, so if it was alpha decay, it would be what's referred to as the daughter nucleus, would have a higher binding energy. Anyway, that is what we see in this case. The binding energy went a little higher. Then part C comes back to the decay process itself and says, what would Q be for this? And don't forget those 2 electrons. That's how many electron masses we need. That gives us a Q value. 0.001289 atomic mass units are missing, and that corresponds to 1.20 MeV of kinetic energy of the products coming out. So I will, let's stop there and take a break. That works fine. And we'll come back, and because we have 5 more problems to look at, and then we'll get those other 5 done also.